Why does the Moon remain in orbit when the space between Earth and the Moon is almost entirely vacuum? The average distance is about 238,855 miles, or 384,400 kilometers. And that span is so large that NASA often explains it by saying about 30 Earths could fit in between. The Moon is not resting on anything across that distance. There is no visible bridge, no cable, no stream of material linking one world to the other. And yet the Moon does not wander away. It keeps following its path, month after month, year after year, while Earth turns below it. That is where the first strain appears in the old everyday picture of gravity. We are used to pushes and pulls that involve contact. A hand presses a table. Wind drives a sail. Water carries a wave. But the Earth, Moon system, does not look like any of those familiar cases. It works across a region that, by ordinary standards, seems empty. That discomfort was already present in the age of Isaac Newton. In 1687, in Philosophia Naturalis Principia Mathematica, Newton gave physics one of its most successful mathematical structures. The same rule that describes a falling body near Earth can also describe the orbit of the Moon and the motion of planets. That was a profound change in human understanding, because it removed the old divide between the sky and the ground. The heavens were no longer governed by one set of rules and Earth by another. One law of gravitation could connect them. Britannica notes that Newton showed the relationship between the motion of the Moon and the motion of a freely falling body on Earth, and from that he built the modern quantitative science of gravitation. But even while the mathematics worked, the deeper physical picture remained unsettled. The rule was precise, the mechanism was not. That difference matters more than it first appears. A mathematical law can tell us what happens without telling us what reality is doing underneath. Newton's gravity said that every mass attracts every other mass, and that the strength depends on mass and distance. For calculation, that was an extraordinary success. It explained Kepler's laws of planetary motion and gave astronomers a dependable tool, but it also carried an unease that later physicists could not ignore. Britannica describes Newton's picture as one in which bodies act at a distance without bodily contact. That phrasing is important because action at a distance is exactly where the mind begins to resist. If nothing material stretches from Earth to Moon, what is the influence passing through? What is being transmitted? What is actually changing from one place to another? Set the mathematics aside for a moment and stay with the scene itself. The Moon moves around Earth at an average orbital speed of about 3,680 kilometers per hour. It is not stationary above us. It is always moving sideways along its orbit. At the same time, Earth's gravity keeps bending that motion inward. If that inward influence vanished while the Moon kept its sideways motion, the Moon would not continue circling Earth. It would move off along a different path. If the sideways motion vanished while the inward influence remained, the Moon would no longer orbit. It would begin falling inward. What we call an orbit is the continuous meeting of those two facts, forward motion and inward bending. NASA's current Earth-Moon data list both the average orbital distance and the Moon's mean orbital velocity, and together they show why an orbit is not a static arrangement but a continuously maintained geometric path. The trouble is that the old language of pulling can hide what needs to be understood. When people hear that Earth pulls on the Moon, the mind often imagines something like a stretched line across space. But no telescope has ever shown such a line, because that is not how modern gravity is described. The distance between Earth and Moon is filled mostly with vacuum, not with a hidden mechanical medium like air carrying sound. Sound needs material particles to pass vibrations from place to place. Ocean waves need water. A shaken rope needs a rope. Gravity does not fit comfortably inside that family of examples. That is why the Earth-Moon system feels unsettling when examined carefully. It behaves in a way that ordinary contact-based experience does not prepare us for. Newton himself understood the scale of what he had done, but the theory left a door open. It could predict motion with astonishing power, yet it did not close the gap between measurement and physical picture. That gap became harder to tolerate after the rise of special relativity in the early 20th century. If no influence can outrun light, then a gravity law that seems to let masses affect one another instantaneously across any distance becomes conceptually unstable. Britannica's explanation of general relativity states this directly. Newton's theory requires an unspecified action at a distance through which separated bodies pull each other instantaneously, and that conflicts with the relativistic structure introduced by Albert Einstein. A new account of gravity became necessary, not because Newton's numbers suddenly failed in ordinary cases, but because the old picture did not sit comfortably with the deeper architecture of space and time. This is where the central paradox sharpens. We call space empty because it contains so little matter compared with the solid surfaces we know. But empty, in that ordinary sense, does not mean physically featureless. Einstein's work moved gravity out of the category of ordinary forces and into the structure of spacetime itself. Stanford's Gravity Probe B material states the idea plainly. Einstein identified the property of spacetime responsible for gravity as its curvature. NASA's relativity material makes the same transition in more practical terms, explaining that particles, planets, stars, and even light move on the stretched and curved structure of spacetime. In that picture, Earth is not sending a mechanical pull through a void the way a hand might tug a cord. Instead, Earth changes the geometry in its neighborhood, and the Moon moves within that geometry. That shift takes time to absorb because our instincts are built from local experience. In ordinary life, a straight path feels obvious, but in relativity, straight has to be defined inside spacetime itself. A body moving freely does not need a visible shove every moment. It follows the path made available by the geometry it occupies. Near a massive object, that geometry is not the same as it would be far away from mass. So the Moon's orbit is not well described as a body being yanked around by an invisible rope. It is better understood as motion through a space-time geometry that is not flat. Stanford's explanation of space-time says gravity feels strongest where space-time is most curved and vanishes where space-time is flat. That does not make gravity unreal. It makes the old force picture incomplete. The familiar Earth-Moon distance helps here, because it is large enough to expose the weakness of the contact analogy. If the Moon were only a few miles away, the mind might still cling to a picture of direct attachment. But at nearly 250,000 miles, the emptiness between the two bodies becomes too obvious to ignore. NASA's educational Earth-Moon modeling material points out that diagrams often draw the two much closer than they really are, because accurate scale is inconvenient on a page. Once that true separation is restored, the old image begins to fail. And that failure is productive. It forces a deeper revision. Gravity is not best understood as something pushing on matter from the outside through a material link. The modern view asks us to look at motion, distance, and time together. There is another useful correction hidden inside this. The Moon is not fixed at one exact distance every moment. Its orbit is slightly elliptical, and NASA lists an orbital eccentricity of about 0.0554. The average distance gives a stable summary, but the real orbit changes over time. Even so, the larger pattern remains stable enough that eclipses, tides, and orbital predictions can be calculated with very high precision. That combination of variation and long-term regularity is one of the reasons gravity became such a powerful science. The system is not rigid, it is structured. And once that is recognized, the emptiness between bodies no longer looks like a blank failure of explanation. It looks like the place where explanation must be improved. So when we ask what gravity is actually pushing on, the most honest beginning is that the old wording has already gone wrong. The deeper account does not start with a push through vacuum. It starts with the possibility that vacuum is not the right mental picture at all. Space, in modern physics, is joined with time into a physical structure whose geometry can change. Newton reached the edge of that realization without crossing it. He described the behavior of gravity with a precision that still works extraordinarily well for many purposes. But the Earth-Moon system keeps pressing on the unresolved part. Across a span that appears empty, one world remains in ordered motion around another. The numbers are real, the orbit is real, the success of prediction is real, yet the older image of a force reaching through nothing begins to thin the longer one looks at it. That thinning is where the next layer of gravity begins. Did Isaac Newton explain gravity, or did he do something just as powerful and still incomplete? In 1687, when Philosophia Naturalis Principia Mathematica appeared, Newton changed physics by showing that the same rule could connect a stone falling near Earth, the moon circling Earth, and the planets moving around the Sunday. That was a major unification. Before Newton, the sky and the ground had often been treated as if they belonged to different domains. After Newton, they could be described within one mathematical structure. The achievement was enormous, but the deeper physical basis of gravity remained open, and the tension stayed with the theory from the start. The success of the calculations was undeniable. The underlying mechanism was not. The brilliance of Newton's work becomes clearer when we compare it with the older picture of motion. Johannes Kepler had already extracted accurate laws of planetary motion from Tycho Brahe's observations. Galileo Galilei had studied falling bodies and accelerated motion near Earth. What Newton did was connect those two worlds. Britannica summarizes it directly. Newton discovered the relationship between the motion of the moon and the motion of a freely falling body on Earth, explained Kepler's laws, and established the modern quantitative science of gravitation. That is why the apple and the moon belong together in the history of physics. Not because of a charming anecdote, but because Newton recognized that a body falling downward and a body orbiting overhead can both be understood through the same gravitational framework. This is where the old apple story deserves careful handling. The story is not a cartoon about an apple striking Newton's head. The more reliable historical line comes from later recollections. The Royal Society notes that Newton himself told William Stukely that seeing a falling apple helped inspire his thinking about gravitation, and Stukely later included the episode in his 1752 memoir of Newton's life. So the apple story is not pure invention, but it also should not be treated as if a single falling fruit instantly produced a finished theory. What mattered was the line of thought that followed. If gravity pulls an apple downward, could that same influence extend far enough to affect the moon? That step turned a familiar event into a universal problem. Once Newton took that step, the structure of the argument became remarkably strong. A freely moving object continues in a straight line unless something changes its motion. The moon does not move in a straight line away from Earth. Its path bends continuously. That means some inward influence must be acting on it. Newton saw that the required inward acceleration of the Moon is much smaller than the acceleration of falling bodies at Earth's surface. Yet it fits the same inverse square pattern once distance is taken into account. Britannica gives the comparison clearly. The Moon's acceleration is about 1/3600 of surface gravity, matching the square of the fact that the Moon is about 60 Earth radii away. That was not a loose analogy. It was a numerical bridge. It showed that terrestrial falling and celestial orbit could be treated as one physical process expressed at different distances. That is why Newton's achievement still feels so solid. He did not merely suggest that the same force might govern apples and moons. He showed that the numbers line up. NASA's historical gravity material puts it in compact form. Newton proposed that gravity is universal, that the Sun's gravity holds the planets in their orbits, and that Kepler's laws follow from the inverse square law. This matters because it marks the point where gravitation became more than description. Kepler had described planetary motion very well. Newton supplied a dynamical account that could generate those motions from general rules. That is a deeper level of explanation. And for everyday astronomy, orbital mechanics, and much of engineering, it still works with extraordinary accuracy. But now the incompleteness enters. Newton's law told physicists how the gravitational attraction scales with mass and distance. It did not tell them what gravity is made of, what carries it, or how one mass physically influences another across empty space. Britannica states this plainly. Newton assumed an attractive force between massive bodies that does not require bodily contact and acts at a distance. That phrase, acts at a distance, is the crack that never fully closed. The theory predicted motion brilliantly, but it left open the physical basis of the interaction itself. If Earth and Moon are separated by vacuum, what exactly is happening between them? Newton's mathematics answered the how much of the force. It did not settle the by what means. This gap was not a small philosophical afterthought. It was one of the central reasons the theory remained controversial in the 18th century. The Stanford Encyclopedia of Philosophy notes that Newton's theory of gravity remained under dispute for decades, especially because of the absence of a mechanism, and in particular, the absence of a contact mechanism producing gravitational forces. In other words, many thinkers were willing to admire Newton's predictive success while still doubting that he had given a fully acceptable physical account. For people trained in the older mechanical tradition, forces were expected to arise through contact, pressure, impact, or some material mediation. Gravity did not fit comfortably into that picture. Newton had built a triumph of exact science, but not everyone felt that the conceptual foundation was complete. Newton himself did not fully close that door. His later correspondence and the long debate around it show how uneasy the issue remained. The Stanford Encyclopedia's article on Newton's philosophy explains that readers and critics continued to object to universal gravity because it seemed to leave open precisely the sort of distant action that many thought impossible in nature. Even Newton's own position is not simple. In the Principia, gravity is treated in a way that permits successful calculation. In later discussions, he resisted pretending to know more than the evidence warranted. That restraint is part of his greatness. He did not hide the fact that prediction had outrun mechanism. He accepted the strength of the law while refusing to decorate it with unsupported machinery. That balance between confidence and restraint is one reason Newton still matters so much. He took phenomena that had been observed separately, falling bodies, planetary periods, orbital paths, tides, cometary motion, and placed them inside one mathematical frame. Yet he did not claim to have finished the story in a modern sense. The Principia became an exemplar of scientific success, not because it explained everything at once, but because it connected observation and theory with a precision no earlier gravitational account had achieved. The Stanford Encyclopedia describes it as a seminal work whose ultimate success reshaped the goals of physics itself, turning the search for fundamental forces and lawful relations into the central pursuit of the field. That is a very large legacy. Still, the same source also reminds us that the theory had loose ends in its early decades, and that Newton knew this better than anyone. One detail people often miss is that Newton did not even possess the modern constant form that later textbooks present so neatly. The compact equation familiar today came later. Britannica notes that in observations of celestial motion, the measurable quantity is the product of the gravitational constant and the mass, not the constant on its own, and that Newton first estimated the scale by reasoning about Earth's average density. The later experimental route toward the constant usually associated with gravity came in the late 18th century. The American Physical Society explains that Henry Cavendish's 1798 torsion balance work is now viewed as a route to the universal gravitational constant, though Cavendish himself framed it as determining the density of Earth. That historical detail matters because it shows that Newton's theory began as a structure of proportional relations and dynamical reasoning before it became the polished formula students now memorize. So, did Newton really explain gravity? The most honest answer is that he explained its behavior with a level of accuracy and scope that transformed science, but he did not provide the final physical picture. He unified heaven and earth. He showed that the moon is not an exception to falling bodies, but an example of falling under different conditions. He derived Kepler's laws from deeper principles and made gravitation quantitative. That is not a minor step toward explanation. It is one of the greatest advances in the history of thought. Yet, the unresolved core remained. How does one mass influence another across distance, especially across vacuum, without a visible medium or immediate contact? On that point, Newton gave physics a framework of astonishing power, but not the last word. That is why gravity can feel more solved than it really is. Newton made it calculable. He made it universal. He made it useful enough to guide astronomy, navigation, geodesy, and eventually spaceflight. But calculable is not identical to complete. The old picture still leaves a pressure point that later physics had to confront. Once the mathematics becomes clear, the missing layer does not disappear. It becomes harder to ignore. That opening in Newton's account is exactly where Albert Einstein will enter, not to erase Newton's achievement, but to show that gravity may not be a force in the ordinary sense at all. Why did Albert Einstein stop treating gravity as an ordinary force and begin treating it as geometry instead? He did not make that move to sound abstract. He made it because the older picture had begun to fail in ways that could no longer be ignored. Newton's gravitation was astonishingly successful. It described falling bodies, planetary motion, tides, comets, and the orbit of the moon with extraordinary accuracy. But it also carried a structural problem. Masses seemed to influence one another across distance, as if the effect were immediate. And that sat badly with the newer framework of relativity, where no physical influence should outrun light. By the early 20th century, the problem was no longer only how strongly bodies attract. The problem had become more basic: what kind of thing gravity is. Britannica summarizes the shift clearly. Whereas Newton treated gravity as a force, Einstein showed that gravity arises from the shape of spacetime. That change did not appear all at once. A crucial step came in 1907, when Einstein began developing what he later called the equivalence principle. The insight was simple in form and far-reaching in consequence. On a small enough scale, the physical effects of gravity and the physical effects of acceleration can look the same. Britannica states it directly. General relativity follows from Einstein's principle of equivalence, according to which, locally, it is impossible to distinguish between physical effects due to gravity and those due to acceleration. If that is true, then gravity may not belong in the same category as pushes, pulls, and fields in the older mechanical sense. It may instead be telling us something about the structure within which motion unfolds. A familiar thought experiment makes the pressure of that insight easier to see. Imagine a sealed elevator far from stars and planets, moving upward with steady acceleration. Inside, a dropped object falls to the floor. From inside the elevator alone, without looking outside, that event can resemble what happens in a gravitational field. Now turn the situation around. Put the elevator at rest near Earth. The dropped object again falls to the floor. If local experiments cannot distinguish those two cases, then gravity may not be best understood as a separate force acting through space. Einstein took that seriously. He began to suspect that what we call gravitational motion might instead be motion in a space-time structure that is not flat. This is the conceptual pivot. The path from Newton to Einstein is not a rejection of precision. It is a deeper demand for consistency. At first, this can feel like a change in language more than a change in physics. But it is much more than that. In Newton's picture, a planet or moon is pulled away from the straight path it would otherwise follow. In Einstein's picture, the meaning of straight path itself changes near mass and energy. Space-time is not a neutral background that simply sits there while matter moves across it. According to Einstein, matter and energy alter the geometry of space-time, and free bodies move according to that altered geometry. Stanford's Gravity Probe B material puts the core idea in compact form. Einstein identified curvature as the property of space-time responsible for gravity, and gravity feels strongest where space-time is most curved. NASA's overview for the centenary of general relativity says essentially the same thing. Gravity can be described as curvature of space-time caused by massive bodies. This is where John Archibald Wheeler's summary earns its place. He compressed the modern picture into a sentence that became famous because it is both short and accurate. Space-time tells matter how to move. Matter tells space-time how to curve. That line is useful because it separates two roles that older gravity language tended to mix together. Matter and energy do not merely sit inside space and time. They influence the geometry. Then, motion follows from that geometry. Wheeler's sentence is not the full theory, but it captures the direction of the change better than the old picture of an invisible pull extending through emptiness. Still, the phrase curved space-time can mislead if it is taken too literally. It does not mean space is bending into some larger external room. It does not mean the universe is a stretched sheet floating inside something else. That rubber sheet image can help as a first step, and Stanford uses it with caution, but it is only a guide. Real space-time in general relativity is four-dimensional, not a two-dimensional fabric sagging downward because of gravity from some outside direction. The real change is deeper. Distances, durations, and the allowed paths of motion are no longer arranged as they would be in flat space-time. Britannica emphasizes this by calling Einstein's view geometric gravitation. The essential difference is not a new material rope or invisible fluid, but a different geometric structure for the world itself. Once that is said clearly, ordinary orbital motion looks different. Earth is not circling the Sun, because the Sun sends out a hidden tug in the old everyday sense. Earth is moving through the curved spacetime associated with the Sun's mass. The Moon is doing the same in Earth's gravitational environment. A body left to itself in relativity still follows the nearest thing to a straight path available to it. But in curved spacetime, those paths do not look straight when seen from the old Newtonian intuition. An orbit is not a body being continuously yanked sideways by a material connection. It is a body following the geometry available to it. Stanford's educational guide states it plainly. Matter follows the structure of spacetime, and orbital paths require that spacetime be curved. Einstein did not arrive at this by taste or metaphor. He was pushed there by physical and mathematical pressures. Special relativity had already united space and time into spacetime and placed a firm limit on signal propagation. Newtonian gravity, taken literally, allowed gravitational influence to act without delay. That tension could not simply be ignored. At the same time, the equivalence between gravitational and inertial mass, already known from experiment, suggested that gravity was connected to the structure of motion itself in a more intimate way than other forces. General relativity, completed in 1915, answered both pressures at once. Gravity was no longer an external agent acting inside a fixed arena. The arena itself became dynamical. That is why Einstein's theory feels so different from Newton's, even when both describe many of the same solar system motions very well. The theory gained authority not because it was philosophically elegant, but because it produced testable consequences. One of the earliest major successes involved Mercury. Newtonian gravity explains the orbit of Mercury very well, but not perfectly. The point of Mercury's closest approach to the Sun shifts over time, and a small part of that shift resisted explanation within the older framework. General relativity accounted for the remaining discrepancy. Another major test came from light. If gravity is geometry, then even light, which has no rest mass, should follow curved spacetime. During the solar eclipse of 1919, observations led by Arthur Eddington became famous for supporting Einstein's prediction that light from distant stars would be deflected near the Sunday. Britannica notes that Einstein's theory treats gravity as curvature and predicts such bending of light. These were not decorative details. They were signs that the geometric view was describing the world more faithfully than the older force picture in regimes where precision mattered. Another consequence reaches even closer to daily life. Time itself runs differently in different gravitational conditions. In general relativity, clocks deeper in a gravitational well run more slowly relative to clocks farther away. That effect is not a philosophical add-on. It has measurable consequences and must be included in systems such as satellite navigation. NASA documents on tests of relativity note that time delay and related effects are among the definitive ways to test whether gravity behaves as a geometric entity. A theory that changes the rate of clocks, bends light, shifts orbital precession, and predicts gravitational waves is not merely renaming Newtonian attraction. It is rebuilding the physical picture from the ground up. At this point, the old phrase, "gravity pulls," begins to show its limits. It still works in ordinary conversation, and for many practical calculations, Newton's force law remains extremely useful. Engineers still use Newtonian gravity for a wide range of purposes because it is simpler and accurate enough in weak fields and low-speed conditions. But Einstein's decision was not to throw away Newton's success. It was to reinterpret what that success had been approximating. The geometric theory contains Newtonian gravity as a limiting case under ordinary conditions, while going beyond it where space-time curvature and relativistic effects matter more strongly. NASA's discussion of general relativity makes this point directly. General relativity describes gravitation as space-time geometry, while recovering Newton's description as an approximation in appropriate regimes. So why did Einstein decide gravity was not a force in the usual sense? Because the evidence and the logic kept pushing in that direction. A theory of gravity had to fit a universe where space and time are joined, where local acceleration can mimic gravity, where no physical influence should move outside causal structure, and where precise anomalies demanded a deeper account. The answer he built was severe, not ornamental. Gravity is the manifestation of curved spacetime. Matter and energy reshape the geometry. Bodies and light move within that reshaped geometry. The universe did not need an invisible rope crossing empty space. It needed a different understanding of what space and time are physically doing. That is why Einstein's step still feels so radical. Newton described gravity as a force acting across distance with precise mathematical rules. Einstein changed the stage on which motion unfolds. The result is less intuitive, yet difficult to dismiss once the evidence is considered. The space between objects no longer appears as a passive gap. It becomes part of the physical story itself. This idea brings us to what does it mean to say space can bend if we cannot even see it? What does it really mean to say that space can bend when no one has ever looked out a window and seen space-time itself the way we see water, smoke, or glass? The phrase can sound like a trick of language if it is left too vague. Einstein's theory did not claim that the universe contains a visible sheet floating somewhere behind the stars. It claimed something more exact than that. It claimed that gravity is built into the structure of space-time, and that what changes near mass is not merely the behavior of objects, but the geometry that defines distance, motion, and the flow of time. Britannica summarizes the transition directly. In Einstein's view, gravity arises from the shape of space-time, rather than from a force acting across distance. The first step is to separate the useful picture from the misleading one. Many people meet general relativity through the rubber sheet image. A heavy ball placed on a stretched sheet makes a depression, and a smaller ball rolls around it. That image is not worthless. Britannica says it can provide some insight, but only as a guide and not as a definitive statement of the theory. Stanford's Gravity Probe B material makes the same caution more sharply. The rubber sheet picture helps visualize the spatial side of Einstein's theory, but it leaves out the temporal side, which is essential. So the analogy can open the door, but it cannot carry the full weight of the idea. If it is taken too literally, it starts producing confusion instead of clarity. The confusion usually begins here. A rubber sheet bends downward because Earth's ordinary gravity is already pulling on it. So if someone says gravity is explained by a rubber sheet, the mind may object immediately. What causes the bending in the first place? That objection is fair. The real theory is not saying space-time is a membrane sagging inside some larger room under some external pull. It is saying that the geometry of the world itself changes in the presence of mass and energy. Britannica puts it in more formal terms by saying that space-time near a mass is distorted, and that this distortion defines the natural paths followed by light and matter. The sheet image is only a sketch for one aspect of that geometric change. The actual claim is deeper and less visual. To make that less abstract, it helps to think about what geometry means in everyday life. On a flat sheet of paper, the shortest path between 2 points is a straight line. On the surface of Earth, that rule changes. The shortest path between distant cities is not a line you could draw through the air with a ruler. It is part of a great circle on Earth's curved surface. Britannica uses exactly this comparison when explaining geodesics in curved spacetime. A geodesic is the natural path allowed by the geometry. In general relativity, planets and light follow geodesics in spacetime. That means an orbit is not a body being yanked around by a hidden cord. It is a body following the natural path defined by a geometry that is no longer flat. That phrase, natural path, matters. In Newton's picture, a planet wants to move in a straight line, and gravity keeps deflecting it away from that line by applying a force. In Einstein's picture, the deeper revision is that what counts as straight has changed. Stanford's explanation says this directly. Planetary trajectories are very nearly straight in spacetime, not in ordinary three-dimensional space. That sounds strange at first because daily intuition is trained on space alone, while relativity joins space and time into one structure. If the structure is curved, then a path that is straight in spacetime can appear curved when we only look at its spatial part. That is one reason orbits seem to change character when you move from Newton to Einstein. Now the invisible part becomes more concrete. Saying spacetime bends does not mean there is a hidden material object we have failed to photograph. It means that the rules used to measure intervals are different from place to place when mass and energy are present. The path of light can change. The ticking rate of clocks can change. The route a freely moving body follows can change. Those are not metaphors. They are measurable consequences. Stanford's material states that gravity feels strongest where spacetime is most curved and vanishes where spacetime is flat. It also notes something even more surprising in Earth's weak gravitational field. Much of what we experience as gravity near the surface comes from the warping of time more than from the warping of space alone. In practical terms, clocks on Earth run more slowly than clocks farther away. This is the point where many people realize that curved spacetime is not decorative language. If time itself runs at different rates in different gravitational settings, then gravity is no longer only about where objects are. It is also about how durations accumulate. Near Earth, that difference is small but real. Near a neutron star or black hole, it becomes much stronger. Once time enters the story, the old habit of imagining space as an empty box with a universal clock outside it can no longer survive. Space and time are participating together in the phenomenon. That is why Einstein needed space-time rather than space alone. Space by itself was not enough to explain how gravity changes the world. Light provides one of the cleanest examples because light has no rest mass, yet it still responds to gravity. In the old force picture, that can feel awkward. In the geometric picture, it follows naturally. Britannica explains that geodesics in spacetime define both the deflection of light and the orbits of planets. If spacetime is curved, then light does not need to be pulled in the ordinary sense. It follows the geometry available to it. That is why starlight passing near the Sun can bend slightly, an effect that became famous after eclipse observations in 1919 supported Einstein's prediction. The significance of that result was not only that light bends. It was that geometry, not a hidden rope, had made a testable prediction about the visible sky. The same framework also changes how we think about falling. On the ground, it feels natural to say gravity pulls objects downward. But in general relativity, freefall is closer to unforced motion than standing still is. A falling body follows its natural path through curved spacetime. The reason you feel weight while standing on Earth is not because you are peacefully at rest in the deepest possible sense. Stanford's Space-Time Guide explains the reversal in a striking way. Your weight on Earth is due to the fact that your body is traveling through warped space-time. The ground prevents you from following the free-fall path you would otherwise take. So the experience of weight comes from being held off your natural trajectory, not from serenely following it. That is a major shift from everyday language, but it makes the physical picture more coherent. This also clarifies why astronauts in orbit appear weightless, even while gravity is still strongly present. They have not escaped gravity. They are in continuous free fall around Earth. Their spacecraft and their bodies follow nearly the same space-time path, so there is little internal support force pressing them against the floor. In Newtonian language, one can still describe this as orbital motion under gravity. In Einstein's language, it becomes easier to see why the sensation inside the spacecraft is one of near weightlessness rather than of being heavily pulled downward. The geometry of motion and the local experience line up. The concept becomes less mysterious once the old habit of equating gravity only with a downward tug is relaxed. Another way to make the invisible concrete is to ask what would happen if space-time were truly flat everywhere. Britannica says that in a region distant from massive objects, space-time is uncurved, and both light rays and test bodies would travel in perfectly straight lines. That statement gives the theory a firm comparison point. Flat space-time is not a poetic idea, it is the baseline case. Curvature is the deviation from that baseline produced by mass and energy. So when Earth orbits the Sun, or when the Moon orbits Earth, the curved path is not evidence that some unseen material is tugging on them through a void. It is evidence that the geometry in that region differs from the flat case. Once that comparison is made clear, curvature stops sounding like a mystical extra layer and starts sounding like a measurable property of a physical framework. This is also why the phrase empty space needs care. Space can be empty of air, dust, or dense matter, and still not be physically trivial. In general relativity, even regions we casually call empty inherit geometric structure. They can contain curvature, they can guide motion, and they can transmit changes in the gravitational field as waves. Space.com's overview, summarizing NASA's explanation, states that especially massive objects warp space-time, and that this distortion manifests as gravity. That wording is useful because it keeps the emphasis where it belongs. Gravity is not being added to space-time from outside. It is the way space-time behaves when mass and energy are present. So, when physicists say space can bend, they are not asking us to believe in an invisible cloth hidden behind reality. They are describing a change in the measurable relations that govern motion, light, and clocks. What would be a straight path in flat space-time becomes an orbit in curved space-time. What would move past in a simpler geometry can instead fall inward. What would travel undeviated can bend near a massive body. The invisible becomes concrete through consequences. We do not see space-time directly the way we see a wall or a cloud. We infer its structure from what bodies and light actually do. That is how much of physics works. Electromagnetic fields, atomic orbitals, and quantum states are also known through disciplined inference tied to measurement. Space-time belongs to that same scientific pattern, not a fantasy layer placed over the world, but a precise description earned by what the world repeatedly does under observation. If gravity is geometry rather than an ordinary pull, then changes in gravity are no longer only about strength. They are about how information about geometry travels across distance. That becomes especially hard to ignore when the Sun is placed at the center of the picture and one asks whether Earth would respond at once if the Sun were suddenly gone. That thought experiment cuts straight through the old picture of gravity as an instant pull across distance. The average Earth-Sun distance is 1 astronomical unit, about 149.6 million kilometers, or about 92.96 million miles. Light from the Sun takes a little more than 8 minutes to cross that distance. In general relativity, changes in gravity do not move infinitely fast. They propagate at the speed of light. So if the Sun could somehow disappear, Earth would not know at once. For a little more than 8 minutes, Earth would continue following the space-time geometry set by the Sun as it had been. Only after that light travel time would the change arrive. That is one of the sharpest corrections Einstein brought to gravity. In Newton's law, gravitational influence is written as if one mass responds immediately to another, no matter how far apart they are. Newton's theory works extremely well for many practical calculations, but if taken literally, it suggests instantaneous action across space. Britannica's summary of general relativity states the problem plainly. An instantaneous gravitational response would require propagation at infinite speed, and that cannot be reconciled with special relativity. Once Einstein had built a universe in which causal influence is limited by the speed of light, gravity could no longer remain a truly instantaneous reach across the void. Something deeper had to replace that picture. This is why the vanishing sun example matters. It is not really about erasing the sunday. It is about understanding what gravity is allowed to do. If gravity were an ordinary pull acting directly through empty space with no delay, then Earth's orbit would respond at the same instant the Sun changed. But general relativity does not describe gravity that way. It describes gravity as the geometry of spacetime, and changes in that geometry move outward causally rather than appearing everywhere at once. NASA's Hubble material describes gravitational waves as ripples in spacetime that propagate at the speed of light. That statement does not apply only to dramatic collisions of black holes. It reflects the deeper rule that gravitational information respects the same causal structure as other physical influences in relativity. At first, this can sound almost too neat, so it helps to slow the idea down. The sun you see in the sky is already the sun as it was about 8 minutes ago, because light needed time to reach Earth. The gravitational environment created by the sun also reaches Earth with that same causal delay. So, in the thought experiment, Earth would go on orbiting where the sun used to be, not because physics is confused, but because both sunlight and gravitational change need time to arrive. The delay is built into the structure of spacetime itself. 1 astronomical unit is not just a distance scale used by astronomers. It is also a reminder that causality in the solar system is not instantaneous. Even inside our own planetary neighborhood, information takes time to travel. That brings in a word that matters here more than force: information. When physicists ask how fast gravity travels, they are really asking how fast a change in the gravitational field, or more deeply, a change in space-time geometry, can be communicated from one place to another. A static gravitational field around the sun is one thing. A sudden change in that field is another. The first is the background structure Earth moves within. The second is a signal. General relativity says signals do not outrun light. That turns gravity from an old-style instantaneous pull into something tied to causality, propagation, and the finite speed at which the universe updates distant regions about local events. Britannica's general relativity summary frames exactly this break with Newton's picture. There is an important subtlety here. People sometimes hear, the speed of gravity equals the speed of light. and imagine that gravity must always point toward where the Sun was 8 minutes ago, which would seem to destabilize planetary orbits. But relativity is more exact than that. In a stable system where bodies are moving smoothly and fields are not changing violently, the structure of the equations prevents the kind of simple lag that naive intuition expects. Planetary motion remains stable because the gravitational field of a steadily moving source is not just a delayed arrow aiming at an old position. The full relativistic field includes the geometry and motion together in a consistent causal framework. The 8 minutes later statement applies to changes in the source, not to a crude picture in which Earth perpetually chases an outdated Sunday. The point of the thought experiment is to understand propagation of changes, not to replace Newton with a delayed but still rope-like model. This distinction is built into general relativity's treatment of causality and curved spacetime. For a long time, this remained a theoretical statement supported by the internal logic of relativity and by indirect evidence. Then, gravitational wave astronomy gave physicists a much cleaner way to test it. On August 17, 2017, the LIGO and Virgo detectors observed gravitational waves from the merger of two neutron stars, an event named GW170817. About 1.7 seconds later, space telescopes detected a burst of gamma rays from the same event. The source lay about 130 million light-years away in the galaxy NGC 4993. Because the gravitational waves and the light arrived almost together after such a vast journey, scientists could place very tight constraints on any difference between the speed of gravity and the speed of light. LIGO described the event as the first time a cosmic source was seen in both gravitational waves and light, and NASA reported the same multi-messenger detection. That observation was a turning point because it moved the discussion out of pure thought experiments. If gravity traveled much faster or much slower than light, the arrival times from GW170817 would have differed far more dramatically over 130 million years of travel. Instead, the near coincidence strongly supported the relativistic expectation that gravitational waves propagate at light speed within very tight limits. So when people ask, does gravity travel at the speed of light? Modern physics can answer with much more confidence than before. The theory predicted it, and multi-messenger astronomy gave a direct empirical check. The old language of action, at a distance, became even harder to defend once the universe itself supplied a timed comparison between light and gravitational signals from the same cataclysm. Return now to the Sun and Earth. Earth does not orbit because the Sun is somehow grabbing it across 93 million miles in a timeless way. Earth orbits because the Sun shapes the space-time geometry in its neighborhood, and Earth moves within that geometry. If the source changed, the updated geometry would not appear everywhere at once. It would spread outward causally. That is why the thought experiment feels so unsettling. It removes the last comfort of the old everyday model. Gravity is not acting like a rigid rod passing influence instantly across the solar system. It behaves more like a physical structure whose changes must travel and whose travel time matters. This also helps explain why the example is about more than astronomy. It is really about the architecture of reality. Once influence is finite, distance acquires a new seriousness. Cause and effect must respect separation. Now cannot be a universal update command sent across the cosmos. The Sun's current state is not immediately available to Earth, Mars, or Jupiter. Each world responds according to the information that has had time to reach it. General relativity, therefore, takes gravity out of the category of mysterious instant reach and places it inside the same causal discipline that governs the rest of modern physics. The solar system becomes a useful training ground for this idea because the numbers are large enough to expose the delay, but close enough to feel familiar. One astronomical unit, 149.6 million kilometers, a little over 8 minutes for light, and the same causal scale for gravitational change. There is also a deeper emotional reason this example stays with people. We live under sunlight every day, and it is easy to feel as if the sun is simply there in an immediate sense. But even the daylight on your face is already late. The gravitational order holding Earth in its orbit is also already late by the same fundamental rule. Nothing in this weakens the reliability of the solar system. Earth's orbit is stable on human timescales, but it does change the mental picture. The universe is not coordinated by instant awareness across distance. It runs on finite propagation, delayed arrival, and orderly causality. Even our closest star governs us through signals that need time to cross the intervening space. So if the sun vanished, Earth would not feel it instantly. For a little more than 8 minutes, Earth would continue moving as though nothing had changed, because both the light and the changing gravity would still be traveling across space. This is where the modern understanding of gravity becomes clear. Gravity is no longer an immediate pull across distance. Changes move outward at a finite speed, carried through space-time itself. The region between the Sun and Earth is no longer an empty gap. It becomes part of the physical process by which information travels. If gravity needs no medium, then what exactly is crossing the space between two bodies? That confusion begins early because childhood experience trains the mind to expect every wave or influence to ride on something material. Sound moves by compressing air. Ocean waves move through water. A vibration on a rope travels because a rope is there to be disturbed. So when people first hear that Earth affects the Moon across vacuum, or that the Sun shapes Earth's orbit across nearly 93 million miles, the mind naturally starts searching for a hidden substance in between. Modern gravity does not fit that old mechanical expectation. General relativity says gravity is not a force acting through a material medium in the ordinary sense. It is the geometry of space-time itself, and changes in that geometry can propagate outward without requiring air, ether, or any other classical carrying substance. NASA's Imagine the Universe summary states it directly. Gravity arises when mass warps space-time. It is not a force acting at a distance. Stanford's Gravity Probe B material says the same in more structural language. Gravity is strongest where space-time is most curved. That last point matters because the word medium has a very specific history in physics. In the 19th century, many physicists assumed that if light behaved like a wave, it must travel through some invisible substance filling all space, often called the luminiferous ether. That idea collapsed after experiments such as the Michelson-Morley result and after the rise of relativity. Gravity followed a different path, but the older instinct remained. If something can be transmitted, perhaps there must be a material carrier. General relativity breaks with that instinct. It does not propose a hidden fluid or a mechanical mesh stretched through the cosmos. Instead, it treats space-time as the physical framework whose geometry can change. What travels is not a shove in a substance like wind in air. What travels is a change in gravitational geometry. Britannica's treatment of gravitation under relativity makes this break explicit by contrasting Newton's force picture with Einstein's curved space-time description. The distinction becomes easier to feel if we separate two different questions that are often mixed together. The first is, does gravity require contact between pieces of matter? the way sound requires collisions between molecules in air? The answer from modern relativity is no. The second is, does gravity have any physical structure at all, or is it just a word for mysterious, distant influence? Here, the answer is also no. Gravity is not a material medium, but neither is it nothing. The structure is space-time itself. That is why the phrase empty space becomes unreliable once gravity enters the discussion. Space can be empty of air, empty of water, and empty of dense matter, while still possessing geometry, curvature, and the ability to transmit gravitational disturbances. Stanford's Space-Time Guide stresses that space and time are not flat and passive in Einstein's universe. They can be warped by matter. NASA's General Relativity Overview says the same in simpler form. Massive, compact objects warp space-time around them. This helps explain why the analogy with sound fails so quickly. Sound is a mechanical wave. It depends on particles passing pressure changes from one to the next. Remove the particles and the sound cannot travel. A bell rung inside a vacuum chamber becomes silent to an outside listener, not because the bell stops moving, but because the air that would have carried the compression waves is missing. Gravity is not that kind of phenomenon. When physicists describe gravitational waves, they do not mean waves in a gas or in a hidden cosmic liquid. Britannica's summary of gravitational radiation says they are variations of the gravitational field transmitted as waves. NASA's gravitational wave astrophysics material describes them as disturbances in space-time that propagate outward from moving masses carrying energy and momentum. The wave is in space-time geometry itself, not in a separate material filler. That is why the phrase "gravity through vacuum" is both strange and accurate. Vacuum, in modern physics, does not mean a perfect philosophical nothing. It means, at minimum, the absence of ordinary matter in the classical sense. Yet general relativity still allows that region to have structure. A vacuum region can contain space-time curvature. It can guide the path of light. It can influence clock rates. It can also carry gravitational waves. This is one of the largest differences between ordinary intuition and relativistic physics. Intuition treats emptiness as a blank gap. Relativity treats it as a region with measurable geometric properties. Britannica's relativity material explains that a massive object produces curvature in the space-time around it. That around it is crucial. The surrounding region does not have to be full of matter in order to be physically shaped. The older force picture makes people ask, what is the sun pulling on? The geometric picture shifts the wording. The sun is not sending out a grab through a hidden substance. Its mass and energy define the space-time structure in its neighborhood, and Earth moves within that structure. In a stable, slowly changing system, that geometric background is what keeps orbits coherent. In a dynamic system, when masses accelerate violently, changes in that background propagate outward as gravitational waves. NASA's Hubble Science material calls these waves ripples in space-time, moving at the speed of light. That statement is important because it answers the "what is traveling" problem without smuggling in a classical medium. What travels is the changing curvature, the changing geometry itself, not a mechanical pressure wave in matter. There is still a subtle danger here. Saying space-time itself is what changes can tempt people to hear space-time, as if it were just a more respectable name for an invisible substance. That would miss the point. Space-time in relativity is not a material fluid with molecules and friction. It is the relational structure that determines intervals, trajectories, and causality. When that structure changes, the measurable consequences change. Clocks can tick at different rates. Light can bend. Orbits can precess. Gyroscopes can drift in ways Einstein predicted. Gravity Probe B was designed specifically to test two such relativistic effects around Earth, the geodetic effect and frame dragging, and the Stanford Frequently Asked Questions describes them as predictions of space-time geometry, not of a hidden mechanical medium. The experiment matters here because it shows that this is not only language. Geometry produces measurable behavior. Frame dragging is especially useful for this discussion because it reveals that not only mass but also rotation can affect space-time. A spinning Earth does not merely sit inside space-time like a marble in a box. According to general relativity, Earth's rotation drags space-time slightly around with it. That effect is tiny near Earth, but it is measurable, and Gravity Probe B was built to detect it. The very existence of frame dragging shows how far modern gravity has moved beyond the old idea of a static pull through emptiness. A medium in the classical sense is not needed, but the geometry is active enough to be twisted by rotating mass. So empty space near Earth is not physically featureless. It is shaped by Earth's mass and spin. Stanford's Gravity Probe B materials emphasize exactly this point in describing the mission's purpose. Once that sinks in, the childhood confusion starts to loosen. Waves do not all belong to one family. Some are mechanical, like sound in air. Some are electromagnetic, like light, which in modern physics does not require an ether. Gravitational waves belong to yet another category. They are distortions in space-time geometry. That is why comparing gravity to sound can help only for one narrow purpose: to remind us that some phenomena need a material carrier and some do not. Beyond that, the comparison becomes misleading. Sound disappears in vacuum because its medium is missing. Gravity does not disappear in vacuum because the vacuum itself is still part of a geometric spacetime. NASA and Stanford both frame Einstein's theory this way. Gravity is tied to spacetime curvature, not to material transmission through a classical medium. There is another layer here that makes the modern picture more unsettling. In Newton's framework, one could still imagine space as a stage and gravity as something happening on that stage. In Einstein's framework, the stage is no longer separate from the play. Space and time participate. That means the question, what travels through space, is partly the wrong question, because gravity is not always something inserted into a pre-existing empty arena. In the deepest sense available in general relativity, the arena itself changes. Britannica's summary of general relativity says exactly that by identifying gravity with the shape of spacetime. So the language has to shift. Instead of asking what medium gravity uses, modern physics asks what the geometry is doing and how its changes propagate. This does not mean every mystery is finished. General relativity is extremely successful on large scales, but it does not yet tell us how to fully reconcile spacetime with quantum theory. Even Stanford's Gravity Probe B overview notes that general relativity has passed every test so far and still is expected to be incomplete in extreme regimes. So the answer to what exactly is traveling is solid at one level and unfinished at another. At the level of established relativistic physics, what propagates is gravitational information carried by changing spacetime curvature. At a deeper quantum level, the final description remains open. That unfinished edge is real, but it does not return us to air, ether, or ropes across the void. So if gravity needs no medium, what is traveling through space? Not sound like pressure in matter, not motion through a hidden fluid, not a cable stretched between worlds. What travels, in the modern relativistic account, is a change in the geometry of space-time itself. That is why vacuum is not the dead emptiness everyday language suggests. It can be curved, it can influence motion, and it can carry gravitational disturbances outward at the speed of light. Why is gravity the weakest known interaction in nature, and yet the one that ends up ruling the sky? That contrast seems wrong at first. In particle physics, gravity is so weak that it plays almost no role in the internal structure of atoms or in most laboratory-scale matter. NASA's glossary states it directly. Gravity is the weakest of the four fundamental forces in nature. CERN says the same thing in even sharper terms. Gravity is the weakest, though it has infinite range. If that were the whole story, gravity should look like a minor effect, a background detail, something easily overwhelmed by the other interactions. But when the scale grows from particles to planets, stars, and galaxies, the hierarchy changes. What seems weak in the laboratory becomes the large-scale organizer of the universe. The key is that strength alone does not decide which interaction dominates. Range matters, cancellation matters, accumulation matters. The strong and weak nuclear interactions are powerful, but they work only over extremely short distances. CERN's overview of the fundamental forces notes that the weak and strong forces are effective only over very short ranges on the order of subatomic scales. That makes them decisive inside nuclei and particle collisions, but almost irrelevant across the size of a planet, a solar system, or a galaxy. Gravity, by contrast, weakens with distance, but it never truly switches off. It has infinite range. That one property changes everything once the amount of matter becomes enormous. Electromagnetism is the more interesting comparison, because it also has infinite range and is vastly stronger than gravity. If strength were the only factor, electromagnetism should dominate the universe at every level. But ordinary matter is usually very close to electrically neutral on large scales. Positive and negative charges tend to balance. A rock, a planet, or a star contains immense numbers of charged particles, but most of those charges cancel out overall. Gravity does not cancel that way. Mass and energy do not come in positive and negative forms that neatly neutralize one another in everyday astrophysical systems. Gravity is effectively always attractive for ordinary matter, so when enough mass is gathered together, every bit adds to every other bit. Britannica captures this contrast well. Gravity is by far the weakest known force in nature, yet through its long reach and universal action, it controls the trajectories of bodies in the solar system and the structures and evolution of stars, galaxies, and the whole cosmos. This is the first major reason gravity wins on cosmic scales. It is weak, but it never stops adding up. A subatomic particle barely notices gravity compared with the electromagnetic or nuclear interactions around it. A dust grain does not do much better, but an entire planet made of trillions upon trillions of particles presents a different situation. The tiny gravitational attractions between all those pieces accumulate into something enormous. The result is not subtle. The Sun's gravity organizes the planetary system. NASA's heliophysics education material says the Sun's gravity influences the orbits of planets, comets, asteroids, and moons. That is already enough to show how a weak interaction can become structurally decisive once mass is gathered in large amounts and spread across vast distances. The second reason gravity becomes sovereign is that it is not merely additive, it is also self-organizing. Gravity pulls matter together, and when matter gathers, gravity grows stronger in that region, which pulls in still more matter. That feedback does not mean everything collapses without limit. pressure, rotation, radiation, and quantum effects can resist it in particular settings. But it does mean gravity is very good at building structure from diffuse beginnings. In stars, gravity gathers gas until density and temperature become high enough for nuclear fusion to ignite. In galaxies, gravity helps organize stars, gas, and dark matter into long-lived systems. On the largest scales, gravity shapes clusters, filaments, and the cosmic web. NASA's astrophysics materials describe the large-scale structure of the universe as a cosmic web, and gravity is one of the central reasons matter did not remain evenly spread after the early universe. That point often gets missed because gravity feels so ordinary near Earth. A dropped object falls. A person has weight. A planet orbits a star. These are familiar effects. Their familiarity can hide the deeper fact that gravity is the only fundamental interaction that stays competitive over the largest distances while also remaining universally relevant to bulk matter. CERN's educational summary says gravity acts over infinite range, whereas the strong and weak forces are confined to tiny scales. Once the scene shifts from nuclei to the sky, the short-range forces no longer have room to dominate structure. They remain essential inside matter, but they are not the main architects of orbital systems or galaxies. Gravity is. A star shows this division of labor clearly. The strong force helps bind atomic nuclei. Electromagnetism shapes atomic structure and radiation. The weak interaction participates in nuclear processes such as beta decay and fusion chains. But the star itself exists as a star because gravity gathered the gas in the first place and continues to hold the whole object together against internal pressure. Britannica notes that gravity controls the structures and evolution of stars. That is exactly the right scale to notice the difference between being locally strong and globally decisive. Nuclear forces matter intensely in a star's core, but they do not assemble a star across millions of kilometers. Gravity does that. The same logic extends to galaxies. Electromagnetism can shape plasma, magnetic fields, and energetic events inside galaxies, but the long-term orbital structure of billions of stars is governed overwhelmingly by gravity. This is true even though gravity is individually feeble between small objects. The sheer amount of mass involved, combined with gravity's range and one-directional accumulation, gives it authority at galactic scale. Britannica again is useful here because it says gravity controls the structures and evolution of galaxies and the whole cosmos. In other words, the weakness of gravity is a microscopic statement, not a cosmic verdict. There is also a historical reason this can feel counterintuitive. Much of modern physics education begins with atoms, charges, and quantum particles, where gravity looks negligible. In that setting, the statement, "gravity is the weakest force," sounds almost like the end of the story. But astrophysics reverses the emphasis. On large scales, the most important question is not which force dominates at a femtometer or inside a proton. The question is which interaction still matters across thousands, millions, and billions of kilometers, while acting on entire bodies rather than isolated particles. Gravity answers that question better than any other interaction. NASA's materials on planets and orbits, and Britannica's summary of cosmic structure both point to the same reality. Gravity is the framework within which large astronomical systems arrange themselves. Another subtle reason gravity becomes dominant is that it does not just move objects around. In general relativity, it defines the geometry of spacetime. That means its large-scale role is deeper than the old Newtonian image of a pull. Gravity sets the overall shape of motion. the paths of orbiting bodies, the bending of light, and the evolution of cosmic structure. Britannica's discussion of curved spacetime emphasizes that Einstein did not merely modify the strength law, he changed the physical meaning of gravity itself. So when gravity becomes the architect of the universe, that does not mean only that it drags matter inward. It means the large-scale geometry of the cosmos is inseparable from gravitation. There is even a useful paradox hidden inside this. The very weakness of gravity helps some cosmic structures survive. Because gravity is gentle compared with the violent microscopic forces, it can organize matter over long times without instantly tearing ordinary structures apart. Planetary systems can remain stable for billions of years. Stars evolve over millions to billions of years. Galaxies can persist and interact over enormous cosmic intervals. A much stronger long-range attractive force acting universally on matter could produce a far less orderly universe. Gravity's mildness at small scales and persistence at large scales turn out to be a powerful combination for building durable structures rather than only catastrophic collapse. That is an inference from how stars, planetary systems, and galaxies actually behave under known physics. So the sentence, "Gravity is the weakest force," is true, but incomplete in a way that easily misleads. It is true in particle, scale comparisons. CERN's materials say exactly that. NASA's glossary says exactly that. But the second half matters just as much. Gravity has infinite range, acts universally on mass and energy, and does not usually cancel away on large scales. Those three facts let it dominate the architecture of the visible universe. It governs orbits, shapes stars, binds galaxies, and helps form the large-scale cosmic web. Weak in the laboratory does not mean weak everywhere. It means that the importance of a force depends on scale, range, and the kind of matter arrangement being considered. That is why gravity keeps winning where the universe is largest. The strong force is powerful, but confined. The weak force is important, but short-ranged. Electromagnetism is extremely strong, but usually neutralized in bulk matter. Gravity is faint between particles, yet relentless across distance and perfectly suited to cumulative structure. Once enough mass exists, it begins to write the large-scale order of the cosmos. And when that order is disturbed violently enough, spacetime itself can carry the disturbance outward, which is where the next part moves from elegant theory into direct evidence. Can spacetime itself really carry motion, or has physics simply chosen a beautiful way to speak about gravity? That doubt remained open for a century, because curved spacetime is easy to describe in words and much harder to catch in measurement. A planet orbiting a star can still be pictured in older ways. Light bending near the Sun can still be described as a path being redirected. Even Mercury's orbit can sound like a correction to Newton, rather than a direct encounter with spacetime itself. What changed the situation was the arrival of gravitational wave astronomy. On September 14, 2015, the two advanced LIGO detectors recorded a signal now known as GW150914. It came from two black holes spiraling together and merging far beyond our galaxy. That detection was announced on February 11, 2016, and it provided the first direct observation of gravitational waves, a phenomenon Albert Einstein's general relativity had implied a century earlier. The event turned curved spacetime from an elegant framework into something measured on Earth. The importance of that date becomes clearer if we go back to the beginning of the prediction. In 1916, Einstein published the relativistic analysis that led to gravitational waves as a theoretical consequence of his field equations. The basic idea was severe and unfamiliar. When massive bodies accelerate in certain ways, they can produce traveling disturbances in space-time geometry itself. These are not sound waves moving through gas. They are not vibrations in a hidden mechanical ether. They are changes in the gravitational field, or more deeply, propagating distortions of space-time. LIGO and Caltech both describe gravitational waves as ripples in space-time, produced by some of the most violent events in the universe. The idea was remarkable in 1916, but for decades it remained difficult to test because the effect is extraordinarily small by the time it reaches Earth. That smallness is the real reason the proof took so long. Gravitational waves carry energy, but they interact so weakly with matter that they pass through entire planets almost undisturbed. This is useful for astronomy because the signal survives the trip, but it is brutal for detection because the distortion produced on Earth is tiny. LIGO's own description of GW150914 explains that the observed strain changed the length of its 4-kilometer interferometer arms by a fraction of a proton's width. That phrase has become famous because it captures the experimental challenge without exaggeration. A passing wave does not shove the detector like wind against a wall. It stretches one direction, while squeezing the perpendicular direction by an amount so small that ordinary laboratory intuition is not built to recognize it. This is where the apparatus matters. LIGO, the Laser Interferometer Gravitational Wave Observatory, operates 2 large detectors in the United States, one in Hanford, Washington, and one in Livingston, Louisiana. Each detector uses laser interferometry along 2 long perpendicular arms to compare tiny changes in distance. If a gravitational wave passes through, the geometry between mirrors changes in a distinctive pattern, altering the interference of the returning laser beams. The 2-detector design is essential because a real astrophysical signal should appear in both places with a small time offset consistent with the waves sweeping across Earth, while local noise should not line up the same way. LIGO and NSF materials explain this experimental design as the core of how the observatory distinguishes genuine space-time signals from terrestrial disturbance. GW150914 was exactly the kind of event the observatory had been built to find. The signal first appeared at Livingston, and then about 7 milliseconds later at Hanford, consistent with a wave moving at light speed across the Earth-scale separation of the detectors. Analysis showed that the source matched the inspiral and merger of 2 black holes with masses of about 36 and 29 times the mass of the Sun, producing a final black hole of about 62 solar masses. The missing mass, roughly 3 solar masses, had been radiated away as gravitational wave energy during the merger. The source lay about 1.3 billion light-years away. These numbers were not guessed from a picture. They were inferred by matching the measured waveform against predictions from general relativity and numerical relativity simulations of black hole mergers. That last point is what makes the detection far more than a technological stunt. LIGO did not merely register an unexplained twitch. It measured a signal whose time evolution, the famous chirp, matched the behavior expected when 2 massive compact objects orbit faster and faster, lose orbital energy through gravitational radiation, and then merge. Frequency rose, amplitude rose. The signal ended in a ringdown consistent with a newly formed black hole settling toward stability. The observational pattern fit Einstein's theory in a direct and highly specific way. The event, therefore, did 2 things at once. It provided evidence that gravitational waves are real, and it showed that strong field general relativity describes the merger dynamics with striking accuracy. For many years, people could reasonably admire general relativity while still keeping it at a distance, as though curved spacetime were a mathematically refined language for things we might one day describe in some other way. GW 1509-14 narrowed that escape. When LIGO measured the signal, the changing distances in the detector were not being explained away by metaphor. Spacetime itself had changed in a measurable pattern. Caltech's announcement said it plainly. The discovery of gravitational waves opens an unprecedented new window onto the cosmos. That sentence mattered because the evidence had crossed from indirect support to direct detection. There had been important clues before this. In the 1970s, Russell Allen Hulse and Joseph Houghton Taylor Jr. studied a binary pulsar system and found that its orbit decayed over time in a way consistent with energy loss through gravitational radiation. That result was strong indirect evidence and earned the Nobel Prize in Physics in 1993. But indirect evidence is not the same as direct observation. The binary pulsar told physicists that the system behaved as if gravitational waves were carrying energy away. LIGO, by contrast, measured the waves themselves arriving at Earth. The difference is similar to the difference between inferring a distant storm from changing sea conditions and directly recording the pressure wave from the storm front itself. NASA and Nobel Materials both frame the Hulse-Taylor pulsar as powerful earlier support, while LIGO marks the direct breakthrough. Once that breakthrough arrived, curved spacetime became harder to treat as merely elegant language. A passing gravitational wave does not transport ordinary matter from source to detector. What it brings is a change in the metric structure governing intervals and separations. That is exactly why interferometers can see it. The distances themselves are altered. In everyday language, one may say, space moved, but the more accurate statement is that space-time geometry varied in a propagating way. LIGO's educational materials explain this with care. Gravitational waves stretch space in one direction and compress it in the perpendicular direction as they pass. That is not a poetic statement. It is the experimentally relevant signature the detectors were designed to record. The discovery also settled a deeper concern left over from earlier parts of this story. If gravity is geometry, then changes in gravity should travel causally rather than appear everywhere at once. Gravitational waves are precisely that kind of traveling change. They are the cleanest known demonstration that gravitational information propagates. Later multi-messenger observations, especially GW 170817 in 2017, tightened the case by showing that gravitational waves travel at the speed of light to extremely high precision. But even before that event, GW 150914 had already shown that violent changes in distant mass configurations do not remain locked at the source. They move across the cosmos and can be recorded here. Another reason the detection matters is methodological. The signal was not accepted because it matched a beloved theory in a vague way. It was tested against instrumental noise, detector correlations, calibration, background estimates, and waveform modeling. The discovery paper in Physical Review Letters laid out those comparisons in detail. This is important for the very question the part asks. Proof in physics is never philosophical certainty in the absolute sense. It is disciplined measurement tied to a theory strongly enough that alternative explanations become far less credible. GW 150914 met that standard. The waveform, timing, detector agreement, and parameter estimation all pointed in the same direction, Two black holes merged, space-time rippled, and Earth recorded the passage. Once that becomes clear, the language around gravity changes again. We no longer need to say only that mass tells space-time how to curve and matter follows that curvature. We can now add that when massive bodies accelerate violently enough, the changing curvature can leave the source, cross enormous distances, and register as a measurable signal. Space is not a passive emptiness in which gravity somehow acts from the outside. Space-time is an active participant, and in extreme events, its activity becomes observable as radiation. That is the exact point where modern gravity stops sounding like a refined reinterpretation of Newton and starts looking like a different physical world picture altogether. The emotional power of September 14, 2015 came from that shift. A signal began its journey about 1.3 billion years ago, long before complex life on Earth had taken its present form. Two black holes spiraled inward, merged, and released energy in gravitational waves. The disturbance crossed intergalactic space, passed through our galaxy, swept through Earth, and altered a pair of instruments by an amount almost too small to imagine. Human beings had built the apparatus just in time to notice. That is why the event still stands as one of the clearest moments when an invisible part of physics became concrete. And once that first ripple had been caught, the next step was no longer whether space-time could move, but what humanity had actually recorded when two black holes struck the geometry of the universe hard enough for us to hear it. What did humanity actually hear in 2015, when two black holes collided far beyond our galaxy and a signal older than human civilization finally reached Earth? It was not sound in the ordinary sense. Space between stars is too empty for sound waves to travel the way they do in air. What LIGO recorded on September 14, 2015, was something stranger and more exact. A passing change in space-time itself. The event, later named GW150914, was detected at 9 hours 50 minutes and 45 seconds UTC by the two advanced LIGO observatories in Livingston, Louisiana, and Hanford, Washington. The signal came from a black hole merger about 1.3 billion light-years away, and it marked the first direct observation of gravitational waves. In the official announcement, Gabriela Gonzalez captured the scale of the moment in one sentence. This detection is the beginning of a new era. The field of gravitational wave astronomy is now a reality. That sentence mattered because it described more than a successful experiment. It marked the arrival of a new way of observing the universe. For centuries, astronomy had depended almost entirely on electromagnetic radiation, visible light, radio waves, infrared, X-rays, gamma rays. Those forms of radiation reveal stars, galaxies, gas, dust, and energetic processes. But a black hole merger can hide much of its drama from ordinary telescopes. Gravitational waves offer a different route. They carry information not about glowing surfaces, but about the motion of mass in extreme gravitational conditions. The LIGO press release emphasized this directly. Gravitational waves carry information about their dramatic origins and about the nature of gravity that cannot be obtained from elsewhere. That is why GW150914 was not just a confirmation of Einstein. It was the opening of a new observational channel. To feel the full significance, it helps to reconstruct what happened at the source. Two black holes, one about 36 times the mass of the Sun and the other about 29 times the Sun's mass, had been orbiting each other for a very long time. As they circled, they emitted gravitational radiation and slowly lost orbital energy. That caused them to spiral inward. Near the end, the motion accelerated violently. Orbital frequency rose. The bodies came closer. The curvature of space-time around them changed more rapidly and more intensely. Then the two black holes merged into a single final black hole of about 62 solar masses. The difference, roughly 3 solar masses, was released as gravitational wave energy in a fraction of a second. LIGO's official release states these numbers clearly, and they remain among the most arresting in modern astronomy. That conversion is worth pausing over. 3 solar masses is not a decorative amount of matter. A single solar mass is already about 2 times 10 to the power of 30 kilograms. To convert around 3 solar masses into gravitational wave energy in such a short interval means the merger briefly produced a power output estimated at about 50 times that of the entire visible universe. As stated in the LIGO press materials, that number does not mean the event outshone the universe in ordinary light. It means that in gravitational wave power, during that final instant, the merger was immense beyond ordinary comparison. The event did not need to be nearby to matter. It was so powerful that even after traveling about 1.3 billion years, the signal still reached Earth with a measurable signature. And yet, the measurable signature on Earth was astonishingly small. This is one of the reasons the discovery feels so intimate despite the scale of the source. A signal from colliding black holes crossed intergalactic space, passed through our galaxy, moved through Earth, and altered the LIGO detectors by less than 1/10,000th the diameter of a proton, according to the LIGO news release. That phrasing is not meant to dramatize the result. It is the experimental reality. The 4-kilometer arms of the interferometers changed in relative length by an amount so tiny that only decades of advances in laser stability, mirror isolation, vacuum systems, and data analysis made detection possible. A cosmic event of extraordinary violence announced itself on Earth, not as a crash, not as a flash, but as a near imperceptible shift in measured distance. This is why saying humanity heard black holes collide is both metaphorical and defensible. LIGO measured the signal as a changing strain in space-time, not as airborne sound. But once the waveform was extracted, its changing frequency could be translated into audio. That translated chirp became famous because it compressed a deep physical story into a form the human ear could follow. Low frequency at first, then rising rapidly as the orbit tightened, then the abrupt end of merger and ringdown. The hearing was therefore not the direct arrival of sound from space. It was the conversion of measured gravitational wave frequency into audible range. Even so, the emotional effect was powerful because, for the first time, the universe's changing gravitational geometry had been captured as a time-varying signal humans could inspect, analyze, and even listen to after translation. The signal was not imagined. It was measured. The timing between the detectors added another layer of reality. Livingston recorded the event first, and Hanford saw it about 7 milliseconds later. That delay matched the travel time expected for a genuine astrophysical wave sweeping across Earth at light speed. A local disturbance, an earthquake, a truck, an electrical glitch would not naturally produce the same correlated pattern in 2 widely separated detectors with the right waveform and timing. The agreement between the instruments was one of the reasons confidence rose so quickly. LIGO's analysis did not rest on a single, unusual tremor. It rested on detector coincidence, waveform consistency, background rejection, and comparison with predictions from general relativity. The event looked like what the theory said a black hole merger should look like. What makes this more than an engineering achievement is the length of the journey. The signal was emitted about 1.3 billion years ago. That means it left its source long before humans existed in anything like modern form. Continents on Earth were arranged differently. The organisms alive at that time were not waiting for LIGO. The wave crossed a universe that had no obligation to become measurable by us. Then, in one brief interval in 2015, human instrumentation had finally become precise enough to register the distortion. This temporal scale changes how the discovery feels. The universe had been sending the signal all along, though not intentionally, and the limiting factor was never whether the message existed. The limiting factor was whether a civilization could learn how to detect it. That is why Gabriela Gonzalez's sentence carries weight beyond celebration. This detection is the beginning of a new era. The phrase is not only about one paper or one observatory. It is about a shift in method. Before GW150914, gravitational waves were a consequence strongly supported by theory and by indirect evidence, especially the orbital decay of the Hulse-Taylor binary pulsar. After GW150914, they became part of direct observational astronomy. The universe could now be studied through distortions in spacetime itself. The LIGO announcement framed this clearly, and the phrase "new era" has remained attached to the event because it was accurate, not because it was ceremonial. The discovery also changed the status of black holes. Before 2015, black holes had strong indirect support through X-ray binaries, stellar motions near galactic centers, and theoretical consistency. But GW150914 revealed two black holes in the act of merging. This was not inference from matter orbiting an unseen object. This was the dynamical signature of the black holes themselves as they reshaped spacetime and coalesced. LIGO's press kit says that colliding black holes and gravitational waves had been predicted, but never observed together in this direct way. The event therefore gave gravitational astronomy two gifts at once: the first direct detection of gravitational waves and the first direct observation of a binary black hole merger. There is also a philosophical correction inside this moment. Earlier parts of this story asked whether curved spacetime was only elegant language. GW150914 forced a harder answer. A theory can be elegant and still wrong. What protected general relativity here was not beauty, but measurement. The waveform matched the theory's strong field predictions. The detectors agreed. The inferred masses were consistent. The tiny distortions in spacetime were recorded on Earth. A geometric theory of gravity had produced a signal that could be treated as data. That is a different standard from conceptual appeal. After September 14, 2015, space-time curvature was not only something physicists used to describe orbits and light bending. It had become something dynamic enough to ring across the cosmos and reach a terrestrial instrument. The emotional peak of this discovery comes from the contrast between scale and delicacy. At the source, two black holes were merging in an event of immense power. At the detector, the effect was a minute geometric tremor. Between those two ends lay 1.3 billion years of travel through intergalactic darkness. The signal did not need a material medium. It did not need light. It did not need to strike matter dramatically to announce itself. It needed only spacetime, causality, and an instrument sensitive enough to notice what changed. That is why the discovery still feels unusually human. It was not only the universe revealing something. It was humans reaching a level of precision where a distortion smaller than a proton's width could be trusted as evidence of a black hole collision in the distant past. So what did humanity hear in 2015? Not ordinary sound, but the first direct detection that opened the era of gravitational wave astronomy. The signal came from two black holes that merged about 1.3 billion years ago, sending a brief distortion through spacetime that instruments on Earth could measure. For the first time, scientists observed the universe through gravity itself rather than through light alone. And once that new way of observing had begun, attention turned toward a deeper reality. Even after such a breakthrough, gravity still remains incomplete at its most fundamental level. If gravity can bend light, hold planets in orbit, slow clocks, and send waves across the universe, why do physicists still say the deepest part of the story is missing? Because one of the great achievements of modern science is also one of its most incomplete. General relativity has passed every major test thrown at it in the large-scale world of stars, planets, black holes, and cosmic geometry. It explained Mercury's extra-orbital precession, predicted the bending of light, described gravitational time dilation, and led to gravitational waves that LIGO later detected directly. NASA and LIGO both present these as part of the theory's extraordinary success. But that success does not automatically make it final. The trouble begins when gravity is pushed down into the microscopic domain, where the rest of fundamental physics is described by quantum theory rather than classical spacetime geometry. That is the central difficulty of the closing part. General relativity is not wrong in the ordinary sense. It is one of the most successful theories ever constructed. LIGO's analyses continue to report that binary black hole signals are consistent with general relativity in the strong field regime, and NASA has long treated gravitational waves as one of the theory's major confirmations. In that large-scale arena, the theory is not fragile. It is powerful, predictive, and repeatedly confirmed. The missing layer appears because modern physics is built on two foundational frameworks that describe reality in very different ways: general relativity for gravity and large-scale spacetime, and quantum mechanics for matter, radiation, and the microscopic world. Each works astonishingly well in its own domain. The problem is that they do not yet fit together into one complete account of gravity at the deepest level. This is not a minor technical annoyance. APS physics describes finding a quantum theory of gravity as one of the great unsolved problems in modern physics. CERN Courier frames it similarly, noting wide agreement that major outstanding problems in both the Standard Model and general relativity point toward a more complete theory of quantum gravity. That language matters because it shows the issue is not a fringe preference or a philosophical extra. It is a central unfinished task in fundamental physics. A theory of gravity that works beautifully for planets and black holes is still not enough if it cannot be consistently joined to the quantum description that explains atoms, particles, and radiation. The tension becomes clearer when the two frameworks are placed side by side. General relativity treats gravity as the curvature of spacetime. Spacetime is continuous, geometric, and dynamical. Quantum theory, by contrast, describes the microscopic world in terms of quantized fields, probabilities, discrete interactions, and uncertainty relations. The Standard Model page at CERN lays out the quantum side of the picture through the four interactions and their particle-based framework, while also noting that gravity sits awkwardly apart from the rest. Gravity is listed as one of the four fundamental interactions, but the Standard Model itself does not incorporate gravity in the same successful quantum way that it incorporates the other interactions. That gap is one reason gravity remains special and unfinished. The reason physicists keep returning to quantum gravity is that nature does not always respect the boundary between large and smooth and small and quantum. black holes push both descriptions toward one another. The early universe does the same. Near extremely high densities and very short distances, the curvature of spacetime becomes enormous, while quantum effects should also become unavoidable. CERN-Courier notes that unresolved paradoxes appear when one tries to understand the quantum properties of the gravitational field, especially in black hole contexts. APS and other physics sources describe the same pressure point more broadly. A complete theory should tell us what happens when gravity itself must be treated quantum mechanically rather than classically. This is why gravity works across empty space is now both answered and not fully answered. On the level of established modern physics, the answer is clear enough to trust. Gravity works across what looks like empty space because empty space is not physically empty in the old intuitive sense. In general relativity, spacetime has structure. It can curve. It can guide motion. It can transmit gravitational waves. It can change clock rates and bend light. All of that has been tested. But the next step, the microscopic constitution of that spacetime, if any, and the full quantum behavior of gravity remains unsettled. CERN-Courier's recent coverage even notes that effective field theory allows reliable low-energy quantum predictions within general relativity despite the absence of a full theory of quantum gravity. That is a very revealing statement. It means physicists can do useful partial quantum gravity work without yet having the final framework. That partial success is important because it keeps the ending honest. Physics is not standing in complete darkness here. It is not the case that scientists know nothing beyond Einstein. Researchers have candidate approaches, mathematical tools, semi-classical methods, and increasingly ambitious experiments. APS Physics has highlighted new tabletop proposals designed to probe whether gravity must ultimately behave quantum mechanically. CERN and Perimeter Institute both present quantum gravity as an active research frontier rather than a forgotten dream. But none of that has yet produced the universally accepted, experimentally confirmed, complete theory that general relativity became for the macroscopic world. There is progress, but there is not closure. And that matters for how the story should end. It would be easy to close this video by saying that Einstein solved what Newton could not. That is true in one important sense and incomplete in another. Einstein replaced action at a distance with space-time geometry, and that was a profound correction. He gave gravity a causal structure, explained why influences do not update the cosmos instantly, and produced a framework whose predictions have repeatedly been confirmed. LIGO's observations, including the continuing tests of general relativity with binary mergers, show how strong that framework remains. But Einstein did not finish gravity for all scales and all conditions. The theory is classical. The microscopic world is not. That mismatch is why physicists still speak of the deepest part as missing. There is also a human reason this unfinished edge matters. A solved science often becomes emotionally flat in memory, as though it were only a list of facts waiting to be repeated. Gravity resists that flattening. The more closely it is measured, the more successful it appears. The more deeply it is examined, the more incomplete it becomes. That is a rare combination. General relativity does not look weak because it lacks a quantum completion. It looks almost unnervingly strong because it keeps surviving tests while still leaving open one of the biggest structural gaps in modern thought. APS Physics, CERN-Courier, and LIGO materials all point in that direction from different angles. Confirmation on one front, incompleteness on another. So where does that leave the original problem of this video? It leaves it in a place more solid than intuition and more honest than finality. Gravity does not need a rope across emptiness. It does not need a classical medium like air or water. It does not act as instantaneous influence in the Newtonian sense. General relativity has shown, and experiment has supported, that gravity is tied to the geometry of spacetime, and that what we casually call empty space can carry structure, curvature, and propagating change. The Sun does not hold Earth in orbit through a magical reach across nothing. Earth moves within a space-time geometry shaped by the Sun, and changes in that geometry obey causality. That part of the answer is no longer speculation. It belongs to tested physics. But the final layer still waits. If space-time has quantum properties, what are they? Is space-time smooth all the way down, or does the classical picture break at extremely small scales? Can gravity be fully quantized in the same deep sense as the other interactions? What happens at the center of black holes, or at the earliest instance of the universe, where curvature and quantum physics should both become unavoidable? APS physics continues to describe quantum gravity as unsolved, and CERN-linked discussions still treat the reconciliation of gravity and quantum mechanics as a central challenge. Those are not the words of a field that has run out of direction. They are the words of a field standing at its hardest boundary. That makes the closing answer less tidy and more worth keeping. Gravity works across empty space because empty space is not empty in the way instinct first imagines. It has physical structure. It can be curved. It can carry gravitational waves. It can shape motion and time. Newton gave gravity exact mathematical reach. Einstein replaced that reach with space-time geometry. LIGO then recorded space-time responding to violent events in the distant universe. Each step made the picture more precise. And yet, the deepest unification, the one that would place gravity fully inside the quantum world, has not arrived. The theory that governs galaxies and black holes still has not been fully joined to the theory that governs atoms and elementary particles. That unfinished edge does not weaken the story. It gives the story its proper scale. We are no longer asking whether gravity is real or whether space-time curvature is only elegant language. Those thresholds have been crossed. The better answer now is that one of the oldest forces known to human thought has become one of the clearest examples of how science advances. First by describing patterns, then by rebuilding the underlying picture, and then by discovering that even the rebuilt picture contains another boundary still waiting beyond it. Gravity is not less meaningful because the last step is missing. It is more revealing because it shows how far explanation can go before it meets the next demand for clarity. And if you have stayed with me all the way to this last stretch of the journey, thank you. I truly appreciate the time you have shared here. If this long exploration brought you something worth keeping, a like or a soft tap on subscribe would mean a great deal to me. It helps me continue making these science stories with care. And if you would like, I would love to know where you are listening from and what hour of the day or night found you here. Your thoughts, your reflections, and your suggestions help me shape these videos more carefully each time. Wherever you are, I hope the rest of your evening is calm, your thoughts feel lighter, and your sleep comes easily. Thank you for being here.